Hello dear students, today we are going to continue with the last topic of this chapter, that is abnormal molar mass and the Van 't Hoff factor. So let us start with these two topics. First of all, we'll study about what is the meaning of abnormal molar mass. Kindly pardon me if my throat is not clear. So let us read it. Sometimes when we try to determine the molar mass of solute by colligative properties, it is found to be different from the normal molecular mass. Means whenever we try to determine the molecular mass of any compound, we calculate it one way, and the second is how do we calculate? With the help of colligative properties. And the second is we can also determine the molecular mass or the molar mass of that compound with the help of certain experiments. What happens is basically in the case of some of the compounds, we see that whatever molecular mass that we have calculated with the help of colligative properties and the molecular mass that we found experimentally are different. Now this phenomenon is known as abnormal molar mass. Now let us take one example to understand it. Suppose we have sodium chloride. When we calculate the mass of sodium chloride, we find it to be 58.5 gram per mole. But when we find it experimentally, we find it to be 32 gram per mole. Why it is so? Why is it 32 gram per mole? It is because of the dissociation of the sodium chloride. Because we know that sodium chloride is a ionic compound. If not also ionic compounds, we can see that there are certainly some of the particles which can dissociate in the sodium chloride, that is sodium and chlorine. So these get dissociated, and because of that, somewhere or the other, the molecular mass of the sodium chloride will change. Similarly, when we talk about acetic acid, the calculated molar mass of acetic acid is 60 gram per mole. But when we find it experimentally, we find double, that is 120 gram per mole. Now, why it's so? It is so because these acetic acid molecules, they associate, means many acetic acid molecules are present in the solution. So two of them will dimerize. In that condition, all of the molecules will dimerize, and we will have more molar mass than expected. So one thing is very clear from these two observations, that when anything gets dissociated, the molar mass will decrease, and when anything gets associated, the molar mass will increase. We can see here. Now we'll study the causes of this abnormal molar mass. The first cause for such abnormal molar mass can be because of the dilution factor. Sometimes what happens is we know that this whole chapter is based on the ideal solutions which are formed when we dilute them. But there are certain cases when the solution is not enough diluted. In that condition, we'll get the different molar mass, because in that condition it is not ideal and it can go association as well as dissociation. The second is when the solute might have undergone association dissociation. Now what happens is that the solute which is present inside the solution, it undergoes association or dissociation. In this condition we had NaCl solution. The solvent was water, but the solute had undergone dissociation. So in the solution, the solute might undergo association dissociation. It has either of the two cases. When it undergoes association and when it undergoes dissociation, these are the two cases. Now we'll see that what are these two cases. Suppose if the solute undergoes association. So whenever the solute is going to associate, means when it is going to form aggregate, that time the number of particles will decrease, because earlier there were two particles present, but these two particles are now united to form a single particle. So this will be considered a single particle. In this case, the number of particles are decreasing, and hence the value of colligative properties will decrease, because we know that colligative properties always depend on the number of particles. Now the particles are associating, that means the number of particles are decreasing, and hence the colligative properties value will also decrease. But with the certain formulas that we had, we know that colligative property is inversely proportional to the molar mass of solute. Means greater the molar mass of solute, lesser will be the colligative properties associated, because if the molar mass of solute is more, then its particles will be less. In that case, the condition for the colligative property will be less. So according to this phenomenon, here we are having the association. So the colligative property was decreasing, hence molecular mass of solute should increase. So molecular mass of solute is shown more. That was the condition in acetic acid when I was saying that when acetic acid undergoes association, means when it dimerizes. In that condition, the molecular mass will be more, means from 60 gram per mole it converted to 120 gram per mole. Now why it happened? Because the particles were less, so colligative properties were less, and colligative properties were less, so molar mass increased. The second case is when the solute undergoes dissociation. Now, in the case of dissociation, the number of particles will increase. As a result, the colligative properties will increase, and hence, because of this inverse relationship, the molar mass of solute will decrease. That's why in condition of NaCl, when it dissociated, so earlier its weight was 58.5 gram per mole, but afterwards when it dissociated, it was showing the molar mass around 30 gram per mole. That means the molar mass of solute decreased due to the dissociation. This is about the concept of abnormal molar mass. Now we'll talk about the next concept, that is the Van 't Hoff factor. Now Van 't Hoff factor is another important term which is denoted by I. Now whenever we calculate the colligative properties, we will always get wrong because the solutes are getting associated or dissociated. So is there any chance to calculate the correct molar mass of solute using the colligative properties even if they are undergoing association or dissociation? So Van 't Hoff was one scientist who discovered a solution. Means he said that now you can easily calculate the molar mass of the associated or dissociated solute also with the help of colligative properties correctly. Means now there will be no problem. Even if the solution has undergone association or dissociation, you will get always the correct molar mass. But how? So you have to multiply that colligative property by the term small I. Now what is this small I? This is a ratio. This is unitless. It is just a ratio. It is the ratio of observed colligative property to the theoretical colligative property. Means experimental upon theoretical. Now you have to learn this. Please don't inverse the things. So whatever is your experimental colligative property or whatever you are observing upon or divided by the theoretical colligative property, or normal molecular mass upon the observed molecular mass. This is the another important thing that you can learn. Now, what is the significance of Van 't Hoff factor? So Van 't Hoff factor significance is that it tells the degree of association or dissociation. For example, if you are calculating the same value and you are getting I greater than 1. If I is greater than 1, then you are going to say that it is the condition for dissociation. Why it's so? Because you see here, if I is greater than 1 means if this is greater than 1, obviously the normal molecular mass should be greater than the observed molecular mass. Now what is this condition when the observed molecular mass is decreasing? When it is decreasing, so it will be dissociation, hence dissociation. If I is smaller than 1, it is association, and if I is equal to 1, then there is neither association nor dissociation. Let us see one question. When molecular mass of any organic acid dissolved in benzene is found using colligative property, the molecular mass comes double of its normal molecular mass. Why? So when we talk about the organic acid which is dissolved in benzene, we come to know that the molecular mass which is calculated by the colligative property is not the same. The observed molecular mass is double. Why it's so? We have already studied this in just previous thing. In the previous page, we saw that when all the organic acid undergoes dimerization, as we saw the case of acetic acid, so because it is undergoing dimerization through the intermolecular hydrogen bonding, so there is intermolecular hydrogen bonding. You can see now what is this concept you studied in the chemical bonding and molecular structure in class 11, this concept where you saw that the two acid molecules have the hydrogen bonding in between them. Now this hydrogen bonding will dimerize them, and as a result what will happen finally, that you are going to get this type of dimerized compound, and this dimerized compound means the number of particles are decreased, so the colligative properties will also decrease but the molar mass will increase. Now there are some of the conditions for the ideal solution, and in the numericals when you are given association or dissociation, how you are going to calculate the colligative properties or the molar mass. The first is, you know this thing, relative lowering of vapor pressure. This was delta P equal to P naught A XA, but in this case you have to multiply this term with I. I is what? It is normal molar mass upon observed molar mass. Second is this elevation in boiling point. Here again multiply by I. Similar is the third and similar is the fourth. You can see one thing, in every one we have multiplied it with I. I is what? I is the Van 't Hoff factor. So let us see further. The exams, what do they do is that they generally give you the value of I and you can use it in the numericals to calculate the answer. But sometimes if they don't give, then there is one option that they will be giving you the molar masses, the normal and the observed. So by putting that in the value, you can calculate the value of I, and then afterwards you can use it in the numericals. The next concept, the third concept, is the degree of dissociation and association, which is the last concept of this chapter. Now this degree of dissociation or the degree of association can be asked in the exams to calculate. Now how to calculate it with the help of I? That is our main question. So these degree of association as well as degree of dissociation is denoted by alpha. This thing you have already studied in the equilibrium in your previous class. Now, what is the meaning of degree of dissociation? Degree. This definition says that the fraction of moles of solute undergoing dissociation in the solution is called degree of dissociation. Means whatever total number of molecules are there or total number of moles are there of solute, out of those total moles, how many moles are undergoing dissociation? That is called as the degree of dissociation alpha. Now suppose we take how to derive it. So there is one derivation. Initially you take 1 mole of a solute which was not dissociated earlier, but afterwards it was dissociated. So initially before the solute was kept, that time it was just 1 mole, and after solute the concentration was actually 0. But after sometimes you see that what will happen is that this solute which it was earlier, alpha part of this will remove and this alpha part will dissociate into n parts. Again I repeat, initially you are having the 1 mole of solute, but after a certain time under equilibrium you will be having some part of the 1 mole removed, that is alpha part will be removed. This alpha part is only the fraction of moles of solute which are undergoing dissociation, and we will represent it by the n alpha. Why n? Because it will dissociate into n number of molecules or n number of particles. This is your condition. Now you know one thing, what were the number of particles before? So before, particles or the number of moles were 1, but what were the number of particles after? You have studied it in equilibrium, you just add these two, that is n alpha plus 1 plus alpha, sorry 1 minus alpha. Now you know what is the formula of I, that is the total particles at equilibrium, means currently this one upon the total molecules or the total moles or the total particles taken earlier. So that is 1 minus alpha plus n alpha, we have put from here, upon 1. Calculating it, you get the value of alpha for the degree of dissociation as I minus 1 upon n minus 1. So this is the degree of dissociation. Now we talk about the degree of association, that is alpha AS, that is alpha association. In this case, this says that the fraction of molecules which are getting associated into bigger particles out of the total particles. Now whatever particles are there, out of that a certain fraction is associated. This associated fraction is only the degree of association. Now there is a relationship between I and alpha association. What is this relationship? Suppose you are having n particles or n moles of A. Now what will happen after a certain time? These will convert into AN. Why AN? Because earlier you were taking the moles. Now these individual were dissociated into n number of particles. So initially you took 1 mole of A and final was 0, but after a certain time what happened was that alpha part of this was removed and it got associated, means the particles are associating. That's why here in the subscript we have written n. Hence the original particles were 1, alpha particles were removed from them, and these get associated, means the particles are decreasing, means alpha particles you took and these alpha particles will now associate. That means what? Alpha particles are associating or alpha particles are now decreasing further. Understanding this concept, see here what we were having. In this slide we were having first alpha particles we removed. Now these alpha particles which were removed from the original particles, now they will dissociate. That's why here n. Because they are not dissociated here, they will dissociate afterwards. That's why we multiplied n here, because the particles are increasing. But in this case, we have the particles decreasing because they are associating. So we write alpha upon n. Now total moles afterwards is 1 minus alpha plus alpha upon n, and previously we had 1. Putting the formula in I, we have 1 minus alpha plus alpha upon n upon 1. That is 1 minus I minus 1 upon 1 minus n minus 1 upon n minus 1. This formula you have to learn the two formulas by heart. These are directly asked in the board examination also. Now let us see some important questions from the same three topics, that is abnormal molar mass, Van 't Hoff factor, and the degree of association and dissociation. Among these three, the most important is Van 't Hoff factor. That's why I have here three numericals for the Van 't Hoff factor. Now see, first says that what should be the value of I for the following electrolytes. Now here we are having the four electrolytes. You are supposed to say the value of I, that is Van 't Hoff factor. Now in this case, you have to directly calculate the value of I. How do you calculate? You have to just see that how many ions will be formed by the individual solutions. Suppose we have KCl. KCl will dissociate into K plus and Cl minus. So you have 1 and 2. You have two ions here. That's why the value of I here is 2. Suppose this BaCl2. So it will form into Ba2 plus, then it will be 1 Cl minus, again 1 Cl minus. So there are total 3 ions. That's why I equal to 3. Then K3PO4. In that condition, you have one ion as PO4 3 minus, and then you will be having 3K plus total, okay, because of this K3. That's why you are having total 4 ions, so I equal to 4. And here K4FeCN6. In this condition, it will be dissociating in this way, that one ion will be FeCN6, this whole 4 minus, this is potassium ferrocyanide, and along with that we'll be having K4, that is, it will be like this way, that will be dissociated with 4 K plus ions. So total how many ions? 4 plus 1, 5. Okay, this is the way to calculate the Van 't Hoff factor for the following. Next question is, which of the following solutions have the highest boiling point? Now you already know one thing, highest boiling point means they are talking about the elevation in boiling point. That is one of the colligative property. Now first of all, just seeing at this word, you have to write the formula. That is what it is, delta TB equal to KB multiplied by M. Now because you are asked with these type of solutions, that's why the formula changes into I dot KB dot M, because these questions are related to Van 't Hoff factor. When you practice more and more, you will easily understand that if they are asking this question, then it is generally for the Van 't Hoff. Otherwise, you cannot calculate easily. So now what you are given here is, you are given here 1 m KCl, 1 m glucose, 1 m BaNO3 whole twice, means the concentration is same. As we know, concentration is same means the number of particles is same. Number of particles is same, then the colligative properties will be same. Colligative properties will be same, so elevation and boiling point will also be same. But we have now the case for Van 't Hoff factor. Van 't Hoff factor is that we multiply it I with this formula. So calculate the I for 3. Here again from this KCl we got I equal to 2. So here it is I equal to 2. Here glucose will not dissociate or associate, that's why I equal to 1. And for this we have how much? See, 1 is the Ba2 plus, and then we'll be having 2 3 NO3 minus ions. So total 3 ions are there. Now you are multiplying this term with I. Okay. So greater is the I, greater will be this term, and greater will be the boiling point. In this case, find out which of the following has the highest Van 't Hoff factor, because highest Van 't Hoff factor will give the highest value to the boiling point elevation. So answer is third. Next question, calculate the amount of KCl which must be added to 1 kilogram of water so that the freezing point is decreased by 2 Kelvin. Now you have to calculate the amount of KCl, means you have to calculate what? You have to calculate the how much amount of KCl is required, that we can put it over here, that we can add it in the solution. So we are told about the, or we are asked about the WB, that is the mass of solute we require, which must be added to 1 kg of water. This is what? This is WA, given mass of solvent. What is MA? Ma is 18 kg. This is clear. And now we are decreasing the freezing point by 2 Kelvin, that is delta Kf. What is the value of delta Kf? Delta Kf will be equal to, delta Tf will be equal to 2 Kelvin. Okay. And one is Kf only. Kf is given as 1.86. Do you know what is the value of Mb? If you calculate the value for KCl. Now see, you are already using Vent off factor. Okay, we'll be using it. So no need to solve it over here. See here, you are not given the molar mass. You have to calculate it. Sorry, you are not given the actual weight which are observed over here. So you cannot use that formula where we were decreasing this value or we were increasing this value due to the abnormal molar mass. You have to just use the I value. Means this delta Tf equal to I multiplied by Kf multiplied by M. This M contains what? Wb, means Wb upon Mb into Wa, and here we have 1000. Means here you just use the actual value, you calculate it. What is it? Is simply, so when you calculate it, it is simply how much? 74.5. so its value is 74.5, that is the MB, molar mass of KCl. Now put the value of I. What will be I? KCl, we've calculated I already. This is 2 into Kf. Kf is what? 1.86. Acha, we have to calculate WB, so we'll send these things there. Means WB equal to, send this all things there. So delta TF multiply by MB multiply by WA upon I into KF into 1000. Now putting the values, we get delta TF is already 2 multiplied by MB. MB is 74.5 multiplied by WA is 1 kg or 1000 I can write upon I. I is 2 multiplied by Kf, 1.86 multiplied by 1000. This got cancelled. Now you can calculate this value. Whatever will be gram per mole. In that way you can solve the value and you can find the answer. This completes your whole chapter. In the next class we are going to begin with the next chapter.